Good day. I would like to continue our lectures, our numerical solution of AC network with the help of SciLab it will be. So, in previous lecture we saw some ideas and demonstration. Now let's take a look on program itself, how it works, how it should be written. Okay, let me switch 1 second. I need this. So I have a small presentation, and it starts with two persons. One is Oliver Heaviside, and the second one, this guy, it's a Charles Patel Steinmetz. People who developed, invented and developed a method, symbolic method, to solve AC network here. So here is schematics I would like to solve. I think you can see how to solve it. First, we need to specify a reference point or base node. I marked it with a green triangle. It's a 0 point, let's say it's a reference point for voltages. In such theoretical schematics, any point can be chosen as a reference. In reality, it may be ground, it may be neutral. So not always I can select this point freely, but in such practical case, I can take any one. So I like this, it will be a reference point. Next step, I need to number nodes. Here will be node 1, node 2, node 3, and 4. Here it is 5 and here is 6. So I have assigned numbers to nodes as I want, and branches also receive numbers. Okay, for example, branch 1, branch 2, and there is the branch 3. What took the branch 3? This one is 10. Oh, this one is number 3. And also I should select a positive direction for a branch. I can do it freely as I want, but it should be done. For example, for the first node, for the first branch, here with the green arrow, I think the positive direction is in this way. For the branch 8, this way, and for the branch 9, also this way. When I have all nodes and branch numbered and positive direction selected, I need to conduct a first incidence matrix. Here is the rule. Zar means branch, means nodes. So if branch inflows, if it is directed into node, I should write -1 at a crossing of column numbered according to the number of branch and row number as a node. So numbering structure: branches, nodes. If branch number, let's say 1, inflows into node 1, I should write -1. If it flows from it, I will write 1. And if there is no connection, I should write 0. Resulting matrix for my network is here. Here it is. It's a first incidence matrix, describes connection between nodes and branch. Please take a note. One node is not numbered. It's a base or reference node. And you don't see a green triangle here because base, we don't need to write a row in the M matrix for a base node. It is not numbered, it's excluded. Okay. I can switch to code. I hope you can see it. Yeah, you can see it. Here is my matrix inside a SciLab code. The next one, this one, the second incidence matrix or contour matrix. It is not always necessary, but for demo purpose I will conduct it. How? First, I need to specify a contour. Take a number of rows. First, take a difference between number of columns and number of rows in your M matrix, in your first incidence matrix. It will give you necessary number of contours. I have selected 1, 2, 3, 4, 5 contours because, look at my matrix. It has 11 branches and 6 nodes. Subtract 6 from 11 and you'll get number of necessary contours. For each contour, here they are A, B, C, D, and E. I also need to select so-called walk-around direction. I should say contour goes, okay, not a contour goes, but some imaginable travelers who will conduct all voltages to write a second Kirchhoff law or Kirchhoff voltage law. The sum of all voltage drops on the contour should be 0. So this guy who will take all voltage drops for A contour will work like this, and for B contour like this, and for C like this, and so on. They all in the same direction. It's not important, we just need to select. We conduct voltage drop clockwise or counterclockwise. Matrix, here is conduction row. Number of column should correspond to number of branch, and number of row should be equivalent to the number of contour. If branch is co-directed or directed in the contour or current direction, we should write +1. If branch is directed in opposition to the contour or current direction, we should write -1. And if there is no connection, so branch do not belong to contour, we should write 0. For my network, here it is a second incidence matrix. Take a look on the schematics, small. A contour, branch 1, no connection, only the branch 1 correspond, the branch 1 belongs to contour D. So, column 1, branch 1, row D1. Branch 2 goes upside against the D contour walk-around direction, so I'm writing -1 and +1 for the D contour, since branch 2, the second, is co-directed with the E contour. So I got this small table. I can select it. Here is a table. It's a second incidence matrix. And here we see this matrix in our code. Next one, this one, EMF vector. It should be a column vector conducted this way. Column vector, row number corresponds to the branch number, and if EMF is co-directed with the branch, we should write it with the plus sign. If EMF is directed against the branch direction, we write it with the minus sign. And we will get such nice table for my schematics. All positive. Case 1, 2, 3 EMFs. It's occurred. They all co-directed. Next one is resistance matrix. Be careful. AC schematics may contain neutral inductances. If two branches are coupled magnetically, it will be say reflected by the mutual inductance. If schematic do not contain mutual inductance, resistance matrix will have elements only on its main diagonal, and we can store only vector of resistance. But if there are inductances, so if pair of network elements, of network branches are coupled magnetically, mutual inductance elements J omega should be written symmetrically. If we, let's say we have branch 1 and 2 coupled, so elements 1, 2 and 2, 1 will reflect this mutual inductance. If schematic will be width. In our case, these schematics do not contain mutual inductance, so we can store elements in a vector. It's preferable to define constant of J omega, square root from -1 multiplied by angular frequency, and write this way. So for capacitance, we write 1 against omega c. For inductance, J omega A, and R for active resistance. Case, it is I can select it in a table form, vector of its impedance for my network. It's conducted by the branch numbers. In my code, K is frequency. I don't know why, but it's 100 Hz. I don't remember why. Okay. Definition of J omega constant and vector of resistance. Yes, the only elements I forgot, these two vectors, current sources. Usually we use I vector, which is conducted very simple by the number of nodes, and if current source, I have one, inflows into node, we write it with a plus sign. If it flows from node, we should write it with a minus sign. So in my case, one current source, 5 amps, from the node 6 to node 3, flows from node 6 and inflows into node 3. It's very simple. But if we do need a contour solution, we need to take more complicated approach. We need to specify so-called additional, or someone called fake contour, for each current source. So here we have current source. So I assume, okay, I'm with my view saying what current from this source flows through 9 and to the branch 9 and 5, to 9th and 5th branch. I have selected this path for the current of this source. Such fake path should be selected or chosen for each current source. And special vector of G should be conducted. Its element number corresponds to the branch numbers. If this fake current flows into is code-directed, flows in the branch direction, we write it with the plus sign. If it flows in opposite direction, we should write it with the minus sign. Here is the additional or fake contour vector G. It is necessary only for contour solution. Okay, now I can perform some checks. Let's take a look how it's done in get a bit more space. First, these three lines, to make this code reusable, I do simple thing. I'm measuring number of nodes. It's a method from Latvian measure skaits, number of nodes, number of branches, and number of contours. The Latvian designation here, the S in Latvian zaro skaits, meaning number of branches, number of contours, contour skaits. I definitely can use built-in transpose function, but to make it more visible, I will need transposed matrix for both for first and second incidence matrix. If you not remember, transpose, it's like rotate 90 degrees. It's when transposed matrix against some original matrix is when we swap numbers of rows with columns. Okay, this one is matrix transpose. Small checks. Maybe I write. Let me call text name. First, multiply of m and n transposed should produce 0. We should see 0. If no 0, matrices are not consistent. Also should give us 0. Maybe okay, save. 1 second, I'll switch. Let's see what happened. This part. See? Yeah, it's okay. So I have checked my first and second incidence matrix. You can see nice zeros. They are consistent, and also I and G vectors. They're okay. Now voltage. I have a result. The node voltage. How did I get it? Number of nodal admittance matrix should be calculated. How? Here it is. Nodal admittance matrix, 3 element vector, and I need to solve a system of linear equations. I need to solve this system of linear equation. Here I'm using the Zeidel technique, it's preparation of matrix and iterative cycle of Zeidel method. But it's not mandatory. You can easily use Gauss or any method of linear system solution you prefer. This one is simple Zeidel. I should use an external function. Okay. I should create an external function of Zeidel, but I didn't. Here, it's a solution with the help of Zeidel second iterative method of linear equation system solution, right? Ludwig Zeidel, created by Ludwig Zeidel. And I get voltages. When I get voltages from the technique called nodal voltage method, I can apply Ohm's law to get, this is Ohm law application, to get branch current. In fact, I have solved a network. But, okay, let's take a bit more job. So here is a contour current, technique of contour current. For the contour current, I need a matrix of contour resistance. I need a vector of contour EMFs. And I will have to solve this linear equation system with the complex coefficients written for the contour current. If you don't remember, idea of the contour current techniques is assumption that each independent contour has a unique self contour current in it. So solution will give me this maybe imaginable contour currents. Real currents, I can easily obtain real currents with the help of transposed second incidence matrix. Where is my code? Contour resistance matrix, contour EMF vector, and solution with the help of built-in Gauss technique. This is it. Gauss. For the contour current, I used built-in Gauss technique. You can use it for node voltage without any problem. So I will get contour currents, I will get real currents, and to check results, I'm calculating the difference between currents obtained by two different techniques. Contour currents, real currents, difference between two techniques. I think it's quite good. What also I can do, I can calculate a power balance. We can assume that all power dissipated or consumed by passive elements should be equal by power supplied by active elements. Passive power elements power. Oh, 1 second, I need to switch. Yeah. Passive elements, contribution of EMF sources, and contribution by sources. Result should be 0. What case I'm conducting sum of specific elements power. I calculate the total EMFs, current, sources. I have summed all powers, active and reactive, and with total I will show the difference and what we will have. Here it is. Passive elements do consume 297 watts, EMF supply 29.88, and current sources 267.42 watts. Totally I have 10 numbers after the comma for active power and 11 for reactive. What is KCL and KVL? I can check with the Kirchhoff law, I can conduct a Kirchhoff law equation. I will not solve it, but I can use it for check. I need such equation system. 1 second, I will show what kind of system I need. It's a Kirchhoff equation system. So here it is, Kirchhoff equation system, and I can check with the help of Kirchhoff's law. Here it is. Check with the Kirchhoff law. You can see very good results. And the last one moment. If I use a contour solution, how can I get a voltage? In theory, I can use this equation, but much easier is to solve a system of linear equation. It's real much easier. This part I also use Seidel technique to solve an equation system. It's an implementation of Seidel technique. No problem. Just let's switch to the main and take a look. Voltages by contour current method. Difference between voltages by contour current method and nodal voltage method quite small, and here is the max difference between them. Absolute value of max difference. Quite precise. So here is the way how I can solve a stable regime of the AC network. So, no problem. Very easy. In reality, if you take a closer look on the stable regime for such, it's maybe teaching and practicing network. For such network, it always ends with a system of linear iteration, and system of linear iteration, without any problem, you can apply any known technique, but it's solvable. It's a Gauss technique. Zeidelin method works well. If you know, if you prefer some other method, no problem. It's a system of linear iteration only moment all coefficients are complex. And we should remember when we operate, when we do something in AC network, more easiest way to get a solution is to apply a complex mass. Okay, I think it's enough for today. If you have some questions, welcome.